Okay, so everyone should see upper left-hand corner, a little red dot, which indicates that we're recording. And with that, let me hand over the presentation to Group 5, and we'll hear from them about their Speed 3D bioprinter.
All right, so good morning, everyone. Welcome. Yes, we are Group 5, and our product is called SPEED, stands for String and Spring Precision Extraction and Extrusion Device. The members in our group today are Josiah, Lucas,
Hello, everyone.
Anthony, Derek, and myself, Brady. So we'll move on to the next slide. So our presentation is going to be composed of a few sections. We have our head shop concept, of course. We're going to go over the overall size and weight, our individual subsystems, all 5 of them. Our customer needs map we'll have included. We'll also have a finite element analysis of the frame of our design. And then we'll go into a little cost analysis, followed by why you should choose our product. So next. So yeah, our headshot concept. The 3 main things that we really wanted to portray with our device were having minimal contact with the microscope, having the ease of assembly and a short assembly time, and then having multiple weld printing capabilities just for greater, more versatile printing purposes. So the main feature of our microscope is having, of our bioprinters is having the microscope being able to look over it as like almost an external attachment. This is because with this, we will be able to avoid some vibrations that could be caused from, the motors, which are attached to the frame, which is the case for a lot of 3D bioprinters that we've seen. And those motors could cause vibrations, which could in turn distort the quality of what you're seeing through the microscope. And moving on to the ease of use and assembly, our bioprinter is composed of already assembled components or very simple components. So this allows for easy assembly. So you can take it to multiple labs without it being over cumbersome. You don't have to risk, breaking anything. And then the way our bioprinter connects to the Nikon Eclipse TI is very simple. So it really just like it says here, involves simply putting the design over the microscope stage. So it's as easy as that. So it's very easy to use, and that was a big factor we wanted in our design. So, and then also lastly, we have 3 different wells on the device. So we have multiple wells that the printing material can come from. This is very beneficial because it can produce a larger volume of cell structure. So having multiple wells is a big advantage for us because you can basically print bigger products. Next. So yeah, our overall size and weight is right here with 16.5 inches by 13 inches by 14 inches. So yeah, our product does not directly attach to the condenser turret. With that being said, we're able to increase the overall volume while still meeting customer needs. The overall size is, like I said, it turns our design into quite a compact design because we have all the customer needs acquired within the actual area of our product, but you can attach external devices. So the weight, we have a fairly lightweight design. It's 15.6 pounds. This includes the smoothie board, which is externally attached. So again, another external attachment. This weight allows this product to be sturdy, but also it's lightweight enough to where it can be compact and moved around. And again, we have external mounting. So next. Now we're going to go into a little description on each of our 5 subsystems. So we have nozzle, self-storage system, our cell extraction device, and of course our X and Y axis movement and our Z axis movement. So, all right, you guys can take it over from here.
All right, so the nozzle subsystem is composed of a steel core, which two different adapters are attached to it, a pipe fitting adapter, a threaded pipe fitting at the top, and a lure to thread adapter at the bottom. And then attached to the lure adapter is a disposable needle. So the needle is, the disposable needle is chosen because their small profile allows a very low Reynolds number when translating through the liquid-like solid, which means that at higher speeds, the Reynolds instabilities are minimized. The needle, of course, has a small cross-sectional area, allowing a small amount of small detailed features to be produced, and the steel in the syringe or in the needle is very resistant to angular deflection with the drag forces that the needle would be experiencing while translating through the substance. And of course, it is also disposable, allowing for near instantaneous sterilization. The rest of the assembly is composed of steel, allowing it to be easily steam autoclaved and sterilized completely. Next. So the cell storage system we chose was just a simple disposable syringe. This again allows it to be instantly sterilized by just throwing it away and replacing it with a new one. So the volume that we chose was 10 milliliters. So after accounting for the volume of liquid, which would be inside of the 40 centimeters of surgical tubing of 1/8 diameter surgical tubing used between the syringe and the printer head, we would have 6 milliliters of liquid left for printing, which is enough for 15 wells. Oh yeah, this is a clarification. We don't have multiple wells. We have the ability to print in multiple wells thanks to our printing extents. So this means that we can print up to 15 wells before refilling. Next. So our cell delivery system is a syringe being pushed and pulled using a lead screw motor. So there's a stepper motor attached to a lead screw, attached to a guide rail and the syringe itself. And the lead screw motor pushes and pulls on the head while the main body of the syringe is secured. So using a NEMA 17 lead screw motor, we can achieve a very small step size using a driver, which allows us to deliver 0.0552 microliters of fluid per step. So, and the motor itself can go faster if we just simply want to reposition the position of the motor so that we replace parts or add and the syringe itself can be replaced with only one screw being detached, that being the one of the screws that holds the syringe into place on the plate using the hose.
Okay, and for the X and Y axis movement system, we rely on a system of strings and springs guided along guide rails, where the strings extend the springs, and in order to pull back in the opposite direction, the strings unwind, allowing the springs to pull back in their original position. Using the following equation specifically for this distance right here, we can figure out the effects the x-axis has on the y-axis movement. This is important because accuracy is one of our greatest concerns. It is one of the reasons why we chose a string and spring subsystem, because among all our decisions, it was the most accurate. And to achieve this accuracy, we are utilizing a 100-to-1 gear ratio NEMA stepper motor that has a tolerance of below 7 micrometers achieved using 2-inch diameter spools. The strain in wires is also calculated as the distance wanted to travel and the force along the string multiplied by its original length divided by the area, the cross-sectional area of the string times its modulus of elasticity. And that equates to the amount of movement needed on the spool to equate to the appropriate amount of distance wanted to move. All right, next. Our Z-axis subsystem, similarly to the X and Y axis subsystem, relies on a string, but instead of a spring to return it to its original position, we're relying on gravity. This ensures constant tension in the string, similarly to the spring mechanism. And we are also using a 1-to-100 reduction NEMA 17 stepper motor. For the same reasons as the X and Y subsystem, it is extremely accurate. The wire is composed of steel due to its high modulus of elasticity and this lower strain. All right. These are our guiding equations for the position system, where force in the Y direction is calculated via the spring force and the tension caused by the string in the Z-axis, the Z-axis string. This equation allows us to appropriately gauge how much force is input into the Y-axis string so we can utilize it in the strain equation to appropriate the amount of wire necessary to prevent movement and instability. Similarly, we also have another equation for the force in the x-axis, the total force caused by all strings and the x-axis spring. This again is to ultimately go into the mechanism to prevent strain, to sort of account for strain. As force changes, strain changes, so this is vital. And then finally, there are two equations, our length equations, specifically for these moments, these lengths right here, which are designed to, these movements change depending on the position of our center needle. And the goal is to be able to determine how much string is needed or how much string needs to be pulled in or let go to prevent center axis movement, which is our ultimate goal when moving another stage. We don't want y-axis stage to move because x-axis stage is moving. All right.
So this slide is just showing our mapping for the customer needs related to the metrics that we desire, and so then it relates to the subsystems that they are referring to, and also what the actual values that we got for our quantified metrics.
An FBA analysis was performed on the frame itself. The weight was taken and approximated to be an equal distribution on the top. Of course, this is not accurate, but it's just to see the effects. As you can see, the maximum deflection was 9.21 micrometers. Next. Second analysis was performed using 4 bearing loads, which would be, which would mount the X, Y, and Z subsystem, and 4 loads on the columns themselves, each representing the weights of the motors. And we have a more favorable result of 1.72 micrometers. And of course, calibration can be used to mitigate this effect. Unfortunately, we weren't able to perform a vibration analysis. However, it would be desirable in the future, but due to the limitations of SolidWorks Student Edition, this was not feasible for us to perform.
All right, let's talk about cost then. The cost of our overall assembly is within the cheapest ones when compared to the other designs. It has an estimated cost of approximately $840. We managed to achieve that by making parts like simple parts, so we can take advantage of symmetry and also the two radius when manufacturing the parts. These prices were a rough estimate, since when we were doing the manufacturing costs, we were just taking consideration the total volume that had to be removed from the different parts. And at the end, we found out that the largest contributors for the price of our design are the linear bearings and the track rollers, that they are the one that aids on the sliding of our design. At the end, we found out that approximately half of the price was due to the linear bearings and track rollers, and then I'll go ahead and go to the next slide, which is why should you pick our design? Our design relies on basic materials. So our design relies on simple materials to maximize accuracy. It is one of the cheapest designs that we can, when compared to the other designs. It's relatively simple to set up because we just have to place it on top of the printer. It has a 4 points of contacts with the floor, so with the anti-vibration table, so vibrations are minimized. And also, like, since we have motors, since we rely on string on the motors, we can easily just swap and change the position of the motors if necessary to reduce vibrations. We didn't do further vibration analysis because of our limited resources. We hope to, and here we end the presentation, and we would like to know if we would like to hear any suggestions to improve our product.
Yeah, questions?
Hey guys, this is Tom Sayer from Northrop Grumman. You mentioned that you kind of went outside your prescribed design envelope. Did you coordinate that with your customer for this project?
Yes, we talked to Professor Traum about the volume and the mass requirement, and we were told that because the design does not mount to the condenser turret itself on the microscope, we could change the custom requirements a little bit, because the mass was mostly due to the mass that would be attached to the condenser turret, and the volume was also because of the condenser turret. So because of that, because we're not attaching to the condenser turret, we can kind of skirt around that a little bit. And yeah, we did talk to Professor Traum about it though.
Okay, other questions for the speed group?
Yeah, I have a one quick question on this. With using the string and spring, and particularly with the springs for return, did you guys take into account friction on those rails and make sure that your springs are able to overcome those forces as well? I might have just missed it when I was during your presentation.
We did. when we did the calculations, we were more focused on the forces of the different springs acting on the overall movement of the assembly. So we didn't really account for the friction of the bearings, but it would be easily done by just adding the force required on the equation for Fy and Fx.
Okay.
With the string, is it sliding along a sharp edge? Do you think it would wear out, or do you have concerns about the string also elongating over time?
We did not consider elongating over time. You mean by would it be elongated due to fatigue? Is that what you're saying? Because we are taking consideration the strain of the strings already for the forces that are being applied to it.
And
Yeah.
also,
I'm sorry. One of the main aspects of design too is that comes with the ease of assembly and all the simple parts. Is strings are very easy to interchange. So over a short, medium, long period of time, depending on the use of the bioprinter, you'll be able to exchange those strings out very easily. So that was just a big thing that we wanted to have in, because if you're using the printer a lot over a short period of time, then you're going to probably want to get some new strings in there, and they're relatively cheap parts, and then they're easy to add in and take out. So just wanted to add that in there.
also adding to the strings there under low tension, extremely, the maximum amount of force placed on one of these strings is around 5 pounds. So, and also if we undergo calibration prior to every testing, I'm pretty sure the strings would hold up to the accuracy and time measurement.
And adding on to that, the question about the wire sliding on a sharp edge, we actually did include some chamfers. Of course, we can also include other more rounded features that would possibly reduce the amount of the sharpness of the edge on which the strings are. Or we could include some sort of pulley if that's not enough too.
Just to follow on from, I think, Elise's point, especially the Z-axis show there on the previous slide, it looks like it's taken a pretty sharp turn. Yeah, so that's somewhere where I would expect that adding a pulley to turn that corner you'd see a big benefit just in terms of the friction and the fatigue on the wire, turning that corner over and over. That's an opportunity to kind of sort of iterate on this design.
Or we could even add a deep fillet along the outside of that circle that could help reduce it as well. So I'm pretty sure, I don't think you can see in the picture, that we do have a tiny fillet around the outside of that circle. It's just very hard to tell with this picture. If we had the model, we could probably show you.
Thanks, guys. I had one more question about the overall assembly. It looks like it's a pretty big frame in relation to the total microscope. How would a person in the lab assemble it, and how long would it take? How many pieces would they have to handle?
We calculated around an hour to on assembly, but one of the benefits of this is once it's assembled, no further assembly is required, except for replacing the syringe and needle. But the overall assembly is only 15 pounds. It was meant to be built once, and it's ready for use at any moment. And it simply, because the overall head, the upper head of the microscope can pull off or can be pushed back, it can easily goes over the microscope. There is 54 specific parts.
So you looked at
utilized.
how like tools can fit in there to get, so that entire top microscope turret like can be removable?
It goes backwards.
With all these and the strings and everything, if a user has to replace those, does that mean each time they will have to calibrate? And how do you go about calibrating to ensure that the system is at a zero position if you have some strings and you need some specific tensions in those, things like that? Did you guys consider all that?
So for zeroing, we were going to use the 3D mapping feature of the microscope to locate the position of the tip of the needle. And then we would just do the printing relative to that position.
Okay, but you have to pre-tighten the strings, right?
Yes.
Okay, and how do you ensure that you'll have the proper tension on those strings at zero and that you don't over tighten or anything like that?
There isn't as much of a problem due to over tightening, as the initial zero's main goal is to provide sort of an accurate measurement of the overall plate. So there is extreme if the string gets too loose and it stops going under tension, then yes, there is a major problem due to the fact that without tension, there would be no guiding force on the rail. So our main goal is to keep the strings in tension for the entire printing process.
Yes, and the actual tension in the string in the wire shouldn't affect the printing process too much, because the positioning is based on the motor position itself. So if the motor can hold its place under the tension from the spring, then the actual tension in the spring itself shouldn't really affect the positioning of the motor. Of course, that's if we consider we have to consider the strain in the actual wire itself. However, that should be relatively low, as this is not too long of a steel wire. It is made of steel. Shouldn't have too much strain.
You've mentioned string a few times and wire. I take it the Z-axis is a wire. Are the others wires as well, or are they some other material?
Okay, we're just using wires. We're just using steel wires for everything. So we just refer to them as strings, but we actually mean wire.
Yeah, it makes a better acronym your way.
Yeah.
Can I ask on the next image? I think you had a picture that's mounted over the microscope. Yeah, there we go. And I noticed that it looks like one of your drive motors is kind of hanging out real tight to one of the adjustment knobs on the microscope. Is that something that's going to interfere with the operation of the scope itself?
Oh, no, when we were making the assembly, we were making sure there were no interferences affecting on the microscope with our design to the microscope. So it might look close, but they are not interfering.
Well, even if it's not interfering, does somebody have access to be able to turn that knob?
I believe there is. I'm sure there will be, but because at the end we can also just move the placement of that motor. So on that corner, we can move it to the other side.
Or move it more towards the center of that side, if that's necessary.
Okay, I hate to cut it in the middle of lively discussion, but we are just a few minutes over time, and the next group is has assembled in their meeting room. So I'm gonna hit the stop button on the record.